3 years ago we worked on this unit, and 3 years ago we don't know we can calculate the polynomial because we not know how by hand is too difficult to calculate. And now, 4 months ago, I find a software for calculate this polynomial. And then at the final of the presentation, I show you how use this software. Okay. Well, first we define generating subspace B of algebra A. This is the spanned by the generators of the algebra, and we call this generating subspace if each element of A is a linear combination of monomials with formats with elements of these A's. Under these conditions, if we define the zero with as the field K, okay, and the others as the spanned, but all of the monomials in this base of length n, then we can see that the algebra is the union of these ANs, which are the sum of the previous. And in this context, we will define the Gelfand-Kirillov dimension as the supremum of over all the vectorial spaces of dimension of finite dimension over the superior limit of this operation. Okay, of this. We take the logarithm of the function that we have as the dimension as vectorial space of this B. Okay, this Bn, and over the natural logarithm of the natural n, and is some difficult because we take the supremum over all the subspaces, but it's possible only pick one. Number doesn't depend of the particular choice of this space, and is well defined. Also, for the case of modules, we can do more or less the same thing, where F is a finite dimensional subspace F of M that generate is generator of M over the algebra A, and the Bn are the same that we define. And we can define also the grading. Maybe no need defining this, but grading of an algebra is a sequence of K subspaces, K is vectorial subspaces of A, such that the direct sum is again the algebra A, and establish this product. Also, with the case with the modules over the algebra, we can do more or less the same, only with this condition additional, this additional condition, and also define a dimension of Gelfand-Kirillov. If we consider these subsets, these subspaces, and this function, over this function, we can also define the Gelfand-Kirillov as ladder. Also, a filtration of a algebra is a sequence of K subspaces, vector subspaces, such that in the 0 we have the one element, and when we multiply this, both of this, a pair of this, we have this property, no? And also the union of all gives again the algebra. Now we can consider the vectorial space associated to this filtration by made quotients by the anterior and take the direct sum and equip it with a multiplication of this way. And this object is called the associated graded algebra associated to this filtration. And for modules, we do more or less the same. We have also a graded associated module, more or less the same thing we can do, and give multiplications of these quotients of the filtration with these quotients of the module. And also call it the graded module associated to the filtration over the algebra, the filtered algebra. Now we define which is an algebra almost commutative. Is almost commutative if exists a filtration A such that the first is K. Also are finitely dimensionals and product of the first, the grade in one, and the associated graded algebra is commutative. If we have these three conditions, we say that is almost commutative. And we can consider also a function, more or less the same. Now I put here m, un matcal m, for do the difference to the other ones, for say that I consider the filtration of the module, and I do the quotients. No? As all are vectorial spaces, I have this equality. Is well known, and it's possible to show that this function is another thing that a polynomial, of course, when we have talk of almost commutative algebra. Only in this case, we have that this function is a polynomial. And this polynomial have some nice properties. For example, this number is called the Bernstein number, and the grade of this polynomial is just the Gelfand-Kirillov dimension of m. This number, the Bernstein number, not depend of the particular filtration of m, but does depend of the particular filtration to the algebra A. And of course, the Gelfand-Kirillov is invariant, is well defined. Ever have the grade n. And we have here a result. If we have an almost commutative algebra A and a module, a left module with Gelfand-Kirillov dimension D, Bernstein number A, and a chain of submodules, strictly chain, with this property, the consecutive quotients are D, all of this, then the Bernstein number is the sum of the others. And the Bernstein number is for up of this length, the length of this chain, okay, is upper bound. And now if I want to talk about the Weil algebra, because this is an important example of an algebra almost commutative. And first we consider the ring of polynomials in n variables, and we define the Weil algebra over this field as a subalgebra of the endomorphisms of the polynomials generated by the operators x and deltas that acting over a polynomial by this form. If is x, only multiply by the monomial, and we have the partial, do the derivative. Also, the action over this ring polynomial can be extends to a field of rational functions of this way, of natural way, by the rail of the rule of the chain. And with all these tools, we obtain an important result. If I pick an polynomial and I define S as a new variable, for example, it could be something new, such as something that don't appear, something that in principle is nothing, and we consider the extension transcendental simple, and we also, as this is a field again, then I can consider the Weil algebra over this field, and I have another symbol. This is not sense, because I again declare a new variable, and I define the action of the differentials over this new of this way, and I can see that is well defined and is a module over this algebra. And I have also this more important result that says that always that I pick an element here in the polynomials, then there is a polynomial in the variable and the new variable, and differential operator in this new variable as a polynomial, but with coefficients in the algebra, with which isn't the same that this other is more small and is more or less as a polynomial in the new variable. Then I say that operator differential is more or less the same that a polynomial in this new variable. And with this property, with this lemma, we can calculate some extension of an analytic function. Again, we pick a polynomial here, and we consider the region such that f is non-negative in the interior and is 0 in the boundary. And we define for any complex number a function by do this one, this exponential complex. And we can see also that the function is locally integrable and a distribution if we consider this expression where this with compact support. Then we can extend this new function to the whole complex plane as function of lambda. With this previous result, this is too useful. The way of do this is exactly this one. This is completely calculable. We can find this very easy, but this other is just the polynomial that we hear here, just here, is the same for the elation for of the polynomial. Okay, for this election, and only we do a change of variable, the lambda by s, and the problem now is find this polynomial. If we find this polynomial, we can extend the function step by step of the complete complex plane, and is also easy to see that this this polynomial B form an ideal in this ring, and here is where we use the software. Okay, this software was made by the University of Kobe in Japan, and is called exactly as is the can is M1, and how you can see appears here. We need a virtual machine in VMware, and download by the site of the University of Kobe this virtual machine, and is pre-installed this packetry. And we use can for do this. The way to do this is first put load all, then put these commands, and this is not too difficult. The difficult or the part where we put the polynomial is this one. We declare how variables we need. Here we declare 3. Maybe we can put 4 variables, but we calculate the Bernstein polynomial in the more small algebra. Okay, then we put these others, FF messages, and this other, and we. Okay, I do this again. Okay, is okay here. Load all, then run, then this one. I think that I can do this. I'm so nervous. Okay, I have an error key. I don't know how to do this thing. I want goat, but I don't remember how. Yes, a virtual machine in VMware. Yes, running in Debian. Oh. I only need. I can again. Yeah, it's. See, yes, it's a free software. Is installed by VMware and is pre-installed this machine and run over this other program. As the screen is more small, I can go to, okay. This one. Okay. This is the program. VMware. Also is in Windows and in Mac. And the way to do this is with an table of examples. We need put this in the terminal in this order, and we declare the polynomial of this way, and the variable says where we calculate the Bernstein polynomial in which algebra. And I try to do this again. Okay, applications. And we need first, okay, load all, then axis run, okay, then we put the polynomial, okay, go good, and then this, and I expect, okay, this correct? The Bernstein polynomial is this one, from here to here. And the other is a parameter of the ideal that we call the. In fact, this Bernstein polynomial is the monic generator of the ideal. And that's all. This is the way to calculate, and could be used for other things, not only for extend functions. And thanks.